Bismillahirrahmanirrahim. Before starting the session, I would like to discuss about the upcoming quiz. So on 5th of August at 1 past 45, we'll have our quiz. So about the syllabus, I would prefer that uh, I have already declared that the syllabus is up to the lecture number 2020, the last lecture. However, I can restrict it up to the Z transform node. The basic Z transform, we have done it, and you can restrict the syllabus up to the magnitude response, as well as we have talked about the phase response from the pole zero locations. So up to that. So if we consider the node, we have this Z transform. We have done it. So after the mid, starting from the mid, after mid to the Z transform, end of the Z transform. After completing this node, we have started the basic design, basic filter design. So you do not need to consider basic filter design for this quiz. It can be taken as the syllabus for the next quiz. If you have any queries or question on the upcoming quizzes, if you have any question. Okay. So please be present in time to use your maximum time for the quiz. Okay, so let me start the session again. Before starting the session, if you have any question or comments on our previous lecture or any lectures. It sounds that everything is good. Everything is going fine. Okay, in the last class, we have already completed these two design. That means we are talking about the FIR, very basic type of filters, and where we have already designed the low pass filter and the high pass filter. The designing of the filter is basically to show, you need to show the magnitude response. You need to show the phase response as well. So this magnitude response also can be mentioned as like this, and also the phase response of that. So the phase response of that filter. In case of FIR filter, we'll find that the phase response, this one is always linear. We have already shown it for the low pass filter and the high pass filter. We have also found, we have also shown that how to find the cutoff frequency, always the magnitude in the cutoff frequency at omega c, the magnitude of that cutoff frequency, h omega, this is equals to 1 divided by √2. That is our condition from which you can find the value of omega c. Okay, so we can proceed more, and in general, we can write in this way by these two equation. We can develop, or we can establish this relation between a low pass and the high pass. So if you can, you have the low pass filter, and then you can build the high pass filter, or vice versa. So you can build the low pass filter, and from there you can build the high pass filter, or if you can build the high pass filter, you can build the low pass filter as well, in a very simple the sign changes of the Z terms. So in general, what we can say, if we have the low pass filter looks like this. So low pass filter is the basic type of filter, and then at the high pass filter, as we know that the high pass filter with respect to, the Z with respect to low pass filter makes Z is equals to minus Z. So make all the Z value is equals to Z is equals to minus Z. from the low pass to the high pass. And of course, the odd powers will changes the sign as well, and it will continue. So it depends on what is the order of the filter. In this case, the order of the filter is n. So here we have the n order high pass filter, converting from the n order low pass filter. Okay, now we can move to the band pass filter. Of course, that is a combination of low pass and the high pass, and that's why we can cascade a low pass filter with a high pass filter by choosing very precisely the cutoff frequency 1 and cutoff frequency 2. So the fundamental thing is you can design the low pass filter and high pass filters. Always we are trying to put the mention the cutoff frequency before starting the design. So the company or some person will order to design some filters. Of course, they will mention few things. One is what is the maximum gain, what is the pass band gain, what is the stop band gain, and what is the cutoff frequency. So those are the 5 information. So one information, what is the pass band gain, that can be mentioned. What is the stop band gain, that should be mentioned, and what is the cutoff frequency. So here, in case of band pass filter, of course, we have 2 cutoff frequency of this kind of filter. Sometimes it might be symmetry, or it might be asymmetry as well. So we are not talking about the symmetry in this course. In the next course, when we'll talk about more deeply on the filter design, we'll discuss on that. Okay, so this is, of course, from our previous experience, we can find that this plus sign shows the low pass filter and the minus sign shows the high pass filter, and we know that what does it mean. So if we cascade those 2 filters, of course we have a band pass filter. A very important point is we are putting an arbitrary value a there, and what is a? It will we have the target to make this amplitude is equals to 1. This is equals to 1, for which case for the maximum h z, the magnitude max, the maximum value of the magnitude should be is equals to 1. And from that point of view, we can choose the value of a. So the example will be given very soon. So from this equation, you can write this equation, and from there, from this equation or this equation, by using the Euler's formulas, you can write this equation. It's very simple. You can write it. Take the common of e to the power minus j omega, then you'll find this equation. And from this equation, what you can find, what is the maximum value of sine omega? This is the magnitude part. This is also the magnitude part, and the other parts are the phase portion. This is for the phase, and this omega, this portion is for the phase. So if you consider only the magnitude part, we have twice a sine omega, where this sine omega, the maximum value, is equals to 1. So we have twice a into 1. So that is the maximum value is equals to twice a. So if you want to make it 1, then what would be the value of a? So the value of a should be is equals to half. So in that way, we have found that we need to choose the value of a is equals to half. So this can be written as half. So our filter, the band pass filter, is equals to half 1 plus z to the power minus 1 into 1 minus z to the power minus 1. That is our filter, a very simple kind of band pass filter. Of course, the target is the maximum value, maximum amplitude of the filter should not more than 1. That should be is equals to 1. Okay, so from this equation, this is our core equation by which we can draw the magnitude response and as well as the phase response. So I'm writing here in the right side, the magnitude part is based on the sine omega, because we have 2 into half, so that is 1 into sine omega. So the magnitude, it depends on basically sine omega, that is a function of sine omega. And about the phase, if you look at, we have the value j, and then we have e to the power minus j omega. So we have j omega, so that gives plus, and since there is a minus, so you have minus omega. It can be, what is the value of j? That is pi by 2 minus omega. So that is the phase function. So what we can expect, what is the magnitude response if we draw the magnitude response? Of course, this looks like a sine signal. There is no exception. So whenever the omega is going high, of course, the magnitude goes high at the value of pi by 2, and afterwards it will again decrease, and we can restrict our calculation up to the pi value, from 0 to pi value. And of course, this is a cutoff. 1 by 2 will find the omega c1 and omega c2. We'll talk about these two terms in the later portion. And we have a small mistake here in this diagram. So try to understand that at omega equals to 0, what should be the value? At omega equals to 0, it actually starts with a pi by 2. So I have shown here it is start with 0, rather it will actually start with a pi by 2. So I'm drawing the magnitude response here again. This is the magnitude response I'm drawing here. So there is a problem here. Of course, that is a linear one, but the starting point here, it shows 0, but that is not true. What would be the value? At 0, omega equals to 0, that will start with pi divided by 2. The magnitude, the phase would be pi by 2. So whenever it proceed at omega equals to pi, what would be the value? It will be pi by 2 minus pi. So that will give you the pi minus pi by 2. So if this is the zero scale, so it will goes like this. So where this is minus pi divided by 2. So here we start with 0 and ended with minus pi. This is not true. It should start with pi by 2 and ended with a minus pi by 2 at the location of pi. So this is omega scale. From at omega equals to 0, the phase is pi by 2. At omega equals to pi, the phase is minus pi by 2. So this is the final one. So this is how you can find the phase of any filter by the equation. Okay. So then if we move to the stop band filter, okay, so before going to the stop band filter, if we talk about the high pass filter, even this is our high pass filter. Whenever we are talking about low pass filter, we have established that, okay, if we cascade two filters, two low quality filters, if we cascade, this is a low pass filter, then we can improve the quality of the filter. So this is a low quality filter, the first one. The second one, this is a high quality filter where we are cascading two filters. If we cascade more low pass filter, definitely the quality of the filter will increase more. The quality of the filter will increase. The quality of the filter will increase more if we cascade the things. Similarly, For the high pass filter, if we cascade two high pass filters, then the quality of the filter will increase more and more by cascading the filters. How to understand the quality of the filter will increase? Always the significant point is the pass band. In the first case, you'll find this is the pass band. The second case, you can find that the pass band is reduced and reduced more and more if you cascade the things. So the narrow pass band shows the quality of the filter will increase. Okay. So what about the band pass filter? If we cascade to band pass filter again, it will give the phenomena like this. The two terms actually came from the two parts. If we cascade more, definitely the quality of the filter, it will increase. As we can understand the last case, the band is reduced when we are cascading three filters. So for all three cases, for low pass filter, high pass filter, and the band pass filter, if we do the cascading, that will improve the quality of the filter. Okay, so in what about the stop band filter? We'll talk about this. So for all three cases, if we cascade the filters, it will improve the quality of the filter. Okay, now come to the point of the band stop filter. So how to build the band stop filter? If we have the band pass filter with Hz is equals to half 1 minus z to the power minus 2, then this is the band pass filter. Then the band pass filter is just the plus sign of that. So we can design the band stop filter just changing the polarity of the z term. Okay, so this is very simple. We can design it with this pole locations at the zero locations in the two points. And so just to mention it in the z plane. Okay, so from there we can write this equation, and from there again, okay, how you got this term? Again, the cos omega, it got the maximum value is equals to 1. From that point of view, we can find that this is basically a, and this a is equals to half. Okay, if you want to draw the magnitude response and the phase response, very simple in a sense that the magnitude, okay, so these two will cancel each other. The magnitude actually follows by this omega. You need to be very careful on this point. Let me write it here. For the magnitude h omega, it is equals to cos omega, and for the phase, this is equals to, there are two terms. Of course, one term that is a minus omega, but we have something special here to consider. Okay, if we want to go for the magnitude response, try to understand that whenever we are starting with the omega equals to 0, it gives definitely 1. So whenever it goes for higher value of omega, it goes like this. If you proceed more, actually it goes like this. But from our previous experience of drawing or representing the magnitude response, what we have done, whenever we have the negative cross or the cross from the positive end to negative end, we need to jump to the other portion. So that means it will be multiplied with 1, and it looks like this. At which point it will actually touch to the value a magnitude is equals to 0. That is at the location of omega is equals to pi by 2. So this is very significant for the magnitude response as well as for the phase response. So in the magnitude response, what we are doing, we are multiplying the each point with -1, and we are representing it as a positive value like this. So that is our overall magnitude response. So what is our overall magnitude response? This is the overall magnitude response. Now comes to the phase response. What is our phase response? It is equals to minus omega. Need to be very careful on this note. So what is the first value at omega equals to 0? At omega is equals to 0, the theta value of course is equals to 0. So it will start from here. So it is of course a linear phase. Whenever the omega is decreasing, the phi value is also decreasing. How long will go? We need to go up to pi by 2. So this is for omega equals to pi by 2. At omega is equals to pi by 2, this theta value is equals to what? This is minus pi by 2. So this is a minus pi by 2. At this point, in the magnitude response, it is multiplied by -1, and in the phase, it should be added 180 or pi. You can say it can be added with pi. So more than that, so it will added the pi. So what is this value? This value, of course, this is equals to minus pi by 2 plus pi. So that is plus pi by 2. That will start it with the plus pi by 2 again. And then whenever you are proceeding at omega is equals to pi, so I'm talking about this point, omega equals to pi. In that case, the value is equals to what? It will proceed, and it actually touches to the 0 value, because always you need to add pi by 2. So naturally we have pi by 2, and then we have a minus the pi value. So minus pi by 2. Minus pi by 2 is the value. Yeah. So it goes up to the 0, 1. So at the location of pi, it gives you a 0 value. This is the folded version. If we talk about unfolded, it can proceed like this. And in that case, of course, the lower value, this value shows minus pi. So conventionally, we always try to make it the folded version for the convenience. So the unfolded version and the folded version both can shown that it is a linear phase representation. Okay. So we need to be careful whenever the magnitude response actually touches the 0 or crossing the 0. In that case, we need to add 180 degree in the phase response. Okay, so this is the important point for the band stop filter. One more important point is here. What is the quality of the filter? We'll talk about this in the upcoming section as well. So if we have a band stop filter, and if we add another band stop filter, conventionally from our previous experience, this should increase the quality of the filter. However, unfortunately, it will not improve the quality. For example, if we cascade the things, the thing will looks like this, because this is a part of low pass filter, this is a part of high pass filter. So whenever you are cascading low pass with the low pass, high pass with the high pass, the magnitude response actually looks like the red line. In this case, if you consider this cutoff value, you will find where is the cutoff frequency. This is the cutoff frequency. So now the bandwidth, previously the bandwidth was like this. This was the bandwidth, and now due to the cascading, the bandwidth is basically increasing. which shows that the quality of the filter will decrease. That will not improve the quality of the filter. So this is exception for low pass filter, high pass filter, band pass filter. For all three cases, you can do the cascading for improving the quality of the filter. However, for the band stop filter, this is not the case. You can't improve the quality of the filter by cascading. You need to change your design. Okay. Now we can move to the simple IIR type filter. So after having one example, we can introduce why we should move to the IIR filter from the FIR filter. So this is our title. We can start with the pole zero location. So in case of FIR filter, we have already mentioned that all the poles are at the center, and the zero, okay, it can be here, it can be there. So for the band pass filter and the band stop filter, we can put other points in different location. Let's say if I want to stop there, we can put the zeros over there, or we can put the zeros like there. So that means this frequency, let's say omega 1, and this is the omega 1, they will stop by putting those zero points. Okay, there are some tools. Okay, there are some tools on the online you can find for designing those pole zero points and to understand the magnitude and the phase response. Let's introduce that at this moment. Okay. Okay. I'll share this site with you. So in this site, what you can find, you can design your filter. Okay, so this is a very simple task to do the things, and you can find a different information. Let me set the things for understanding. Okay, it looks good now. Okay, let me build some filter first of all, and then I will describe one by one. Here, I'm just there are different types of filters can be taken very quickly, designed very quickly. Here in the left side, you will find the Butterworth filter, Chebyshev filter, inverse Chebyshev, Basel filter, epileptic type filter. So this kind of filters would be designed or discussed in the upcoming semester. However, in this case, we will talk about the basic filter. So I'm taking the blank filter here, so we don't have any pole and zero. So if you want to design a low pass filter, of course, what we need a real poles and the real zeros. So let me take zero, just drag and drop. So where at the zero, I'll put the zero on the circle, and one pole, real pole, to the center. So I can put it on the center. If you do it like that perfectly, if you can do it perfectly, okay. Okay, almost I have done it perfectly. So what you can understand here, this is the transfer function. Okay, so let me think about the magnitude response first. Considering the magnitude response, this is the magnitude response. You find that the magnitude, the higher magnitude is this, and it will goes down. The scale is from a 0 to the other value 1. Let me set the things. The full scale, it is not shown the full scale. Just a minute. Struggling. This is the magnitude response you will find. Okay, so the whole scale we can show. Of course, this is a low pass filter, and we can show it there. And this is the magnitude. So magnitudes. And if I want to plot the phase, only the phase, not the magnitude, and erasing the magnitude, you can see that. Okay. So the phase, you can find the phase is definitely linear, and from your previous experience, you can understand the phase is like this. What about the time domain expression? If you can look at this, you can find the time domain. So if you can recall your example, the Hn is equals to half and half, and you can find the time domain expression is there, half and half. You can also find few very interesting part here. Here is that part which actually represent the digital circuit here. So this is the digital circuit, how it should be, how it looks like, as well as the equation here. You can find the equation with the Z-plane representation. You can also, even this is in the structure, you can also find the code as well. So you can find the microcontroller code. So you can also convert it to the, and so this is the C code. You can generate the C code, and the files are there. You can generate those files, and you can convert it to the microcontroller code as well to build the chip. Okay, so you can burn it to the microcontroller for designing the filter. So this is very simple task. You can play with the pole zero locations. Okay, now if we do not need to have this transfer function. So you always try to think about this magnitude and the phase response. Okay, now if we put this 0 to the other part, you'll find that easily this magnitude, the green lines, it actually shifted. So how that will shift it, you can see that. Okay, this is of course the low pass. So from the low pass, the low pass, it is converted to the high pass. And the phase, if you can look at to the purple color, so we can find that the phase is definitely decreasing monotonously. Okay, so what would be the value in the phase response? You will find the scale of the phase. So this is the phase value. So the angle is given in the right side of the phase. Okay. Okay, so we want to see the magnitude and the phase side by side. And if you want to see the time domain response, you can find that this is half and minus half in this section. We have half and minus half in this section. Okay, this is a low pass and the high pass. Now, if we introduce another 0 there, okay, now 2 zeros are there, and you can see the magnitude. I'm just trying to show the magnitude only. You'll find that this is a band pass filter. This is now a band pass filter. You can change the band of the filter by changing these 0 values as well. This is simple band pass filter. What is the time domain sequences, how they looks like, how the structure looks like, This is the structure of a band pass filter, and this is already we found that that is 1 minus z to the power minus 2 is the power of that section. So you can find the pole zero location with respect to that. You can find the magnitude response. What about the phase response? Okay, you can see the phase response of this is the line, black line, and you'll find that okay, this is a phase value is changing. Okay, so we have the phase value from the positive to negative. If you can consider this example, so we have given that example. So I have the mistake here. So it will start with a positive value and it ended with a negative value, and it has been shown here. Okay. Now the band stop filter. So how to put the band stop filter? So in the band stop filter, definitely you don't have you have the zero location rather than the real axis. Okay, so let me take the blank filter, and now we are taking the conjugate zeros. Okay, conjugate zeros. I'm taking conjugate zeros. So this is the conjugate zeros. I need a real pole. I'm putting the real pole at the center. Okay, so you have this conjugate. Okay, let me take only the magnitude response. So this is the band stop filter we have designed. You can see this magnitude response. So whenever they are at this location pi by 2, they will stop actually at the middle of that. Okay, so this axis, this x-axis in the magnitude response, this shows the value of f, small f, from 0 to half, the small f, the value of small f. So this is the value. So this is 0.25, where it actually having the value is equals to 0 according to our pole location. You can see there, if I change the pole locations, zero locations, you can find that how the magnitude response actually been changed. Okay, it can be changed like this. Okay, this is very simple and very nice to handle. Okay, so you have this kind of experience. You can introduce that kind of experience. And on the other, so what about the phase relation? So you can find the phase value is there. Okay, so this is the phase. Okay, this is the phase. If you can recall our lecture, you can find this phase here. Yes, here. This is the phase we have shown, and it is exactly the same as this one. So that is also linear. And you can find the equation. You can find the structure as well. We'll talk about this structure in the upcoming semester. This is not the time to talk about the structure here. Okay. Okay. So this is the tools by which you can play with. Okay. And in all the cases, we are talking about the linear phase, and this is of course the FIR type filter. Okay, moving to the IIR type filter. I will give the link with your lecture, video lecture, inshallah. Okay. So simple IIR type filter. So first we are introducing the zero location and the pole location here. So from there you can write this equation as well. we are introducing the pole here at the location of alpha, and we already putting a 0 over there. So from this part, we can straightforward say that this is of course a low pass filter, because it will pass the frequency at omega equals to 0 and it will block the frequency at omega equals to pi. That's for sure. So this is of course a low pass filter. What is the impact of the pole? That is very important here. So this is the fundamental equation we can write from this pole 0 location. Now we need to normalize that equation with a factor. This is the factor A. So how we can find the value of A? So always the target is, what is the maximum value of this equation? We need to search it. How we can predict that? Where it gives the magnitude maximum value, how we can find that? Of course, by this time we have the idea how to find the magnitude response from the pole 0 location of the z-plane. From there, we can understand that at this point, that means at omega equals to pi, of course the magnitude is 0 because we have the 0 there. So on the other hand, at the location of omega equals to 0, the distance from the 0 to that point is maximum, and that is 2. And the distance from the alpha, that means the pole to that location, is what? That is 1 minus alpha. That is the distance. So this is the magnitude. This is the magnitude portion which actually give you the highest value. So this is the maximum value. At which location? Of course, at omega equals to 0. So then what should be the value of A? A should be the counterpart of that one. So A should be 1 minus alpha divided by 2. In that way, we can find the value of alpha. So how we can predict where the maximum value will achieve for this kind of simple filter? By observing the pole 0 location, you can understand it very easily. However, by this equation, from this equation, you can also find these and these at the location of omega equals to 0, and from there you can find what is the magnitude here. So this is the highest magnitude or the maximum magnitude you may have. So to make it 1, we need to multiply it with the inverse of that one. So it should be 1 minus alpha divided by 2. I believe you understand this part. About the cutoff frequency, how to find the cutoff frequency of that one. So the magnitude response, we can find the magnitude response with this equation, where we just square off the magnitude in the left side, and we found this equation from the Euler's identity or the Fourier conception. You can write it from the trigonometry very easily. On this case, we can note a few things. Here in this equation, let's say equation number 1, what we can find that the magnitude or the magnitude response basically depends on the value of alpha. Whenever the omega is changes, of course, the omega is changes for any case. Let's alpha is equals to 0. That means alpha is at the location of 0. In that case, we have this kind of basic filter. But whenever you are increasing the value of alpha, let's say this is alpha 1, and then we have alpha 2, alpha 3, from the pole 0 location perspective, this was the first pole. Now we are dragging the pole to the unit circle, So this is alpha 1, this is alpha 2, this is alpha 3. That means you are increasing the value of the alpha. If you do so, then what will happen? The quality of the filter is increasing. The quality of the filter is increasing now. And that is the beauty of the IIR type filter. So in case of FIR filter, what we need to do, we need to cascade the filters, the low quality low pass filter, cascade with a low quality low pass filter and more, and it will improve the quality of the filter. What is the problem? The problem is the order of the filter is increasing. So the orders of the filters are increasing. So let's say this is third order filter, third order, third order. So the order is now ninth order filter. However, in case of IIR type filter, just changing. So where is the 0? 0 remains at the same point. Just changing the pole location, you can improve the quality of the filter. And it can be shown here. We have shown that we can take the example from this website. Okay, just look into this. Let's first, I took a filter, blank filter, and just think about this magnitude response. Okay, so just make your concentration on this magnitude plot. So we are taking a real 0 where the 0 is there. So on the unit circle, and where is the pole that is also a real pole. If I put it in the center, so then it is a low pass filter. Only the magnitude response. I'm talking about only the magnitude response. So this is a low pass filter. Now think about this pole is shifting, and you can see that whenever the pole is shifting and very close to the unit circle, the quality of the filter is improving. Of course, the quality of the filter is improving. You can find the quality of the filter is improving. Okay. At the same time, if you want to see what is the time domain response, this is the time domain response. So whenever the pole is shifting to the right, you'll find the time domain response is definitely changing. The time domain response is changing. You need more values are there. Beforehand, very simple filter. You need two samples. Now, whenever you are shifting, you need more samples, the time domain. In that way, you can observe the filter values. Okay. Okay. So that is the main advantage of IIR filter. If you want to talk about the comparison between FIR and IIR. So in case of IIR filter, this is very simple to improve the quality of filter by changing the pole locations. But in case of, so what is, but what is the challenge in case of IIR filter? We'll see that in future as well. The phase location, the phase of that kind of filter, whenever the pole location is changing, or shifting. So in that case, the phase is now non-linear. It becomes a non-linear phase, and that makes a problem. So we'll talk about this kind of problem with other section, not today. Okay. So for this filter, we need to find the cutoff frequency. How to find the cutoff? Again, the magnitude, we have already found the magnitude. The magnitude should be is equals to 1 by root 2. Since that is, we are making the whole square of the two terms, we are making that as well here. So from this equation, we can found it that cos omega c is equals to twice alpha divided by 1 plus alpha square. So omega c, this is omega c, can be controlled by alpha. This is very significant. So you can control your omega c, that means the cutoff frequency, just by controlling the position of the alpha. For a given omega c, we can write, if we know the value of omega c, now if you know the value of omega c, we need to find the value of alpha, and that is the practical case, because your company or some designer basically first what should I call, first significantly put the value of the omega c cutoff frequency. What would be the cutoff frequency for your design? And from there, you can find what should be the pole location of that filter, because the company people do not know what is the pole location and zero location. As a designer, you are trying to find the perfect pole locations. For a given omega c, we can write, this is alpha, of course, from this is a polynomial equation of alpha of second order. So from there, you can find this equation very simply. For the stability, if you can recall, for the stability, of course, this pole location should be inside the unit circle, because we are talking about the causal system. For the causal system, the solution is the exterior. So that's why the value of alpha should be less than 1 for the stability. If you don't care about the stability, then it can be anywhere. So of course, whenever you will design your filter, it should be for the stable case. So this is for the stable case. So for less than 1, which equation will survive? Of course, 1 minus sine omega c over omega c. If you go for 1 plus omega c, it will definitely go, it will move to more than 1 in some point. So the value of alpha should be this for this equation. In this way, you can find the value of alpha. For omega c is equals to pi by 2, you can find the alpha is equals to 0. What means you have the pole at the center. That means it is a FIR filter. So IIR filter, with some condition, it can be moved as the FIR filter. So that means the pole, if it is on the inside on the 0, 0 location, that moves it to the FIR filter. However, if it is moves here, then it is definitely converted to the FIR filter. And now, if we can move to the high pass filter, which kind of high pass filter? This is, of course, IIR pattern of the high pass filter. So we have talked about the low pass filter. Now we are talking about the high pass filter. It is just the opposite of the previous case. So previously, if you can think of the pole location and 0 locations, previously there is a 0 and there is a pole, and now it is shifted there and this is shifted here. So that is the case. So nothing very special. So everything will remain the same. Just the sign will changes because they are changing the location, and of course, according to that, this value will change. Previously, that was 1 plus alpha This is now 1 minus alpha. So the calculation is given here. Of course, where you will get the maximum value. The maximum value will be found at this location, because at this location omega equals to 0. Of course, the value is 0. The magnitude will certainly be 0. At this location, omega is equals to pi. The magnitude will be the maximum one. Okay, so you can analyze this with your own experience, and you will find it. The alpha is equals to this. We have already derived that. You can derive it here as well. What is the value of alpha? And again here, when the value of alpha, the magnitude, it is very close to the unit circle. When this is proceeding to the unit circle, then the quality of the filter will increase. So if I have alpha 1, alpha 2, alpha 3 in this way, so whenever you are going very close to, this is in a negative value, so I should write it like this. When it goes very close to unit circle, of course, the quality, okay, according to this diagram, this is true. Okay. According to this diagram, this is alpha 3, this is alpha 2, and this is alpha 1. So this actually shows the value. Here, let's say this alpha 1 is equals to this alpha 1 is a minus 0.5, and this alpha 3 is equals to 0. So of course, alpha 3 is higher. So in that case, alpha 3 gives a very poor quality filtering, and the alpha 1 gives very high quality filtering when the value is decreasing in this case. So the equation is this one, by which you can find the cutoff frequency. You can change the cutoff frequency according to the value of the alpha. Okay. So in the next day, inshallah, we'll talk about the band pass filter. It needs some more concentration from the equation perspective. So we have completed up to this. That means the band high pass filter of the IIR pattern with a very fundamental ideas. Okay. I believe that is enough for today's class. Thank you for your participation.